This is example 12-10, depth after an hydraulic jump. So we can see water here is flowing from left to right. There's a sluice gate that's backing the water up, and it dips under the sluice gate, and then it's doing a hydraulic jump, and then we're asked to figure out if this hydraulic jump is actually possible, and also what the depth is at this last section right here. It's called YC. It's a little confusing because that's not the critical depth. All right, so maybe we'll leave it as YC. All right, before we can find YC, we need to make sure that this critical jump can happen. For this critical jump to happen, we have to have the velocity at B, or the flow at B needs to be supercritical, right? So to find out if it's supercritical or not, we need to know the velocity of flow. And we're not given that. We're given the depth, but we're not given the flow rate or the width. So we need to find that separately. So what we'll do is we'll do a flow. Basically, we'll do a Bernoulli equation from A to B, both at the surface. So if we do that, we have PA over gamma plus VA squared over 2G plus ZA, so this is a Bernoulli, not energy equation, PB over gamma VB squared over 2G plus ZB. Right, so we're assuming this is a very short transition, so we don't have to worry about any frictional losses and like that. That's why we don't have the energy equation here. All right, so let's go through all these. Let's say datum at the bottom of the channel. At the bottom of channel. What does that mean? That means ZA is equal to 6 meters and ZB is equal to 2 meters. Points A and B in contact with the atmosphere. Atmosphere, which of course just means that PA is equal to PB is equal to 0, and we can assume very slow flow at A means VA is also equal to 0. So if we plug that all into our energy equation, into our Bernoulli equation, then we get 0 at the beginning because there's no pressure. Velocity is so small that we assume it's 0. ZA, we'll just leave as ZA for now. No pressure at B either. Somehow it doesn't want to erase this. Let's erase this directly. So no pressure, plus the velocity is what we want to get, so that's of course still there, 2G, and then ZB. All right, that's easy to solve for VB, of course. So we can say VB over 2, VB squared over 2G is equal to ZA minus ZB, which of course means that VB is then the square root of 2 times G times ZA minus ZB. All right, then we can plug in some numbers. 2 times 9.81 meter per second squared times 6 meters minus 2 meters. And that is equal to 8.8588894 meters per second. Okay, now that we have the velocity, we can find the Froude number, see if it's bigger or smaller than 1. So we can say Froude at B would be VB over G times YB, which is 8.8588894 meters per second divided by 9.81 meters per second squared. At B we have 2 meters. Turns out to be exactly 2. And 2 is of course greater than 1. So that means its flow is supercritical. Which means hydraulic jump possible. Excellent. So now that we know it's possible, we can calculate it. All right, we have our formula. Usually we'd have y2 over y1, but here we have yc over ya is equal to 1/2 and then square root of 1 plus 8 times Froude at B squared, square root of all that, minus 1. And of course, that's why I kind of stumbled there. This should be YB, not YA. There we go. All right, so then if we plug that in, or if we solve it for YC first, YC then be YB over 2 times all this, 1 plus 8 times Froude B squared minus 1. So that'd be 2 meters divided by 2, square root of 1 plus 8 times our Froude number was 2, squared minus 1. Oops. Close that square root. And that is 4.744526 meters, or if we round it to 3 significant digits, we get 4.74 meters, which is exactly the depth that we expected, or that's depth that we would get at this location C right here. Right. If the depth here is 6 meters and 2 meters there, then we can figure out what the depth is over there using Bernoulli and then using the equations that we derived for the hydraulic jump.